In this lesson, we will learn about the different microservice communication styles and how to implement the synchronous communication style via REST and the HTTP protocol. There are basically two ways you can communicate with microservices. The synchronous style, where the client sends a request and waits for a response from the service, and the asynchronous style, where the client sends a request to the service, but the response, if there's any response, will not be sent immediately. So far, we have been using the synchronous communication style when interacting with our services via Swagger UI and Postman. And in this lesson, we will explore how to use it for inter-service communication. We will learn about the asynchronous communication style in a future lesson. When using the synchronous communication style, the client sends a request and waits for a response from the service, which means that the client cannot proceed without a response. You may make this more evident with any of our services if you put a breakpoint in one of our service controller actions, like getAsync in the catalog items controller, start a debug session in VS Code, and then try sending a GET request to it via Postman. You will notice that Postman waits indefinitely for our service to respond. It can't continue until the service responds. Many times, this type of communication uses a blocking thread, meaning that the client is unable to receive any other inputs or perform any other task until the response arrives. But it could also use a non-blocking thread where the client just offers a callback method to the service, so the service can call the client back when the response is available. In this case, the client thread does not block, even when it still waits for a response. There are two approaches currently to use the synchronous communication style. REST with the HTTP protocol, which is a traditional approach and the one that we have been using so far. In REST, the business objects are modeled as resources, and HTTP verbs are used to manipulate them. Also, you usually use XML or JSON to represent the resources. Most clients support REST. The other approach is gRPC, which is a binary message-based protocol in which clients and servers exchange messages in the protocol buffers format. gRPC is becoming increasingly popular because it supports HTTP2 and is more efficient than REST. However, not all clients support HTTP2, which is why in a microservices architecture, gRPC is used mostly internally between the API gateway and the services, or between the services. In the next lesson, we will be implementing synchronous communication between catalog and inventory microservices using REST and HTTP. At this point, when the client requests the items in the inventory back for a user, the inventory service queries its database and retrieves an array that has basic info about each item, including the catalog item ID and the quantity. However, having a list of item IDs does not tell much to our client in terms of what actual items the user has on inventory. Ideally, we would like to get at least the name of each item and hopefully also its description. However, inventory doesn't know such details about the items since that information is owned by the catalog service. One way to address this is to have the inventory service send a GET request to the catalog service to retrieve the details of all the items. Inventory can then combine this additional info with the details it has in its own database to send back the desired more detailed payload to the client. Let's go ahead and implement this approach. Our inventory microservice needs to receive data from the catalog microservice. But before it can do that, it first needs to define the DTO that represents the retrieved catalog items. Now it turns to be that we already have such a DTO that represents catalog items. And if we go to our catalog project, our catalog microservice, and if we go to DTOs.cs, we're going to see that such a DTO is right here. So this is the DTO, item DTO, that represents catalog items when you query for them. So what I'll do is I'll just copy this DTO, copy this, and then I'll go to inventory. Here we are in inventory, and I'll open DTOs.cs, and I'm just going to paste that as initial DTO for the inventory. Now in the case of inventory, we're going to rename this into catalog item DTO, just to not confuse it with inventory item DTO. And for the case of inventory, again, we don't need that many properties when we're querying for catalog items, and you don't have to retrieve everything, or at least serialize everything into inventory. The only thing that we're going to need in this case is the ID of the item, the name, and the description. We don't need price and created date. for our purposes. So I'll remove those. Save this. And now that we have this DTO, we can actually build a client that is going to be able to query for these items from catalog. So I'm going to right click in Play Inventory Service. I'll create a new folder. Let's call it clients. And in this one, I'm going to create a new file that I'm going to name catalog client.cs. Let's give it a namespace. Play Inventory Service clients. Public class catalog client. So in order for our catalog client to be able to talk to any external HTTP endpoint, it needs to use the .NET HTTP client class. So we're going to define that as a class level variable here. Private read-only HTTP client, and I'll import the system.net.http namespace. And now we're going to do dependency injection of this client into our class. So public catalog client, HTTP client, and we'll take that reference. Now that we have that client available, we're going to define the function that's going to actually retrieve the items from catalog. So this is going to be an async function. So let's define it as async task. And what we're going to return is a collection of catalog item DTO. Since the consumer is not expected to modify this collection in any way, we're just going to return a read-only collection of type catalog item DTO. And we'll name it get catalog items async. Let's import missing namespaces for task and for read-only collection and for catalog item DTO. To retrieve the items, we can do that really easily with one line. So we'll do items equals, we'll do await HTTP client get from JSON. Oh, let's change this. Get from JSON async. May need to import another space systemnet HTTP JSON, and we'll deserialize as I read only collection of type catalog item DTO. And then here is where you put the route that you want to access in the invoked REST API. In our case, in the cases of catalog, the route would be under items. And with that, we can go ahead and return the items. That's all you have to do to invoke another a REST API in another service. With that done, it is time to update our inventory item DTO to have this additional information that we're going to collect from catalog. So let's go back to DTOs. And in inventory item DTO, we're going to add a name and a description. But as we do that, as we can see, extension is complaining, and it's because we need to provide those additional members to the construction of inventory item DTO as we transform the inventory item entities. So what we'll do is we're going to receive additional parameters into this method, which are going to be the name and the description. And we'll feed those two into inventory item DTO constructor. There. With that done, we are ready to go to our controller to actually take advantage of this new information. So I'll go to items controller. And the first thing I'll do is I'll get a reference, or I'll define a class level variable for our catalog client. So I'll define private read-only catalog client. Okay, let's import the missing namespace, and let's receive that as dependency injection into items controller. I receive the catalog client, and we'll get the reference. And now that we have that, let's change a little bit how we do our getAsync method. So we'll get rid of these lines for now. And the first thing that we're going to do is to actually retrieve the catalog items. So how do we get the catalog items? Very easily. Now we can do catalog items equals await catalog client dot get catalog items async. That's all it is. Okay, so that gives us all the catalog items in the catalogs microservice. Now we want to get the list of all the inventory items that we have currently in the inventory microservice. So we'll do that via inventory item entities. It's going to be await item repository, get all async, where the item.user ID equals the user ID that we got as a parameter. Okay, so now we have all the catalog items, and then we have all the entities, the inventory item entities for the current user. Now we need to combine these two pieces of information to produce the DTO that we want to return. So to do that, we'll do this. So inventory item DTOs equals inventory item entities. Select, so we're going to do a projection here for each inventory item. We will do this. Let me close that. First, we will look into the collection of catalog items, and we will find the catalog item that corresponds to the current inventory item. So catalog item equals catalog items. That's single. There should be one and only one catalog item where the catalog item that ID should match exactly the inventory item that catalog item ID. And once we have that, we can do the conversion of the inventory item into a DTO. So we will do inventory item, return inventory item as DTO, and then we have to provide the catalog item that name and the catalog item that description. And finally, now that we have the inventory item DTOs, we will return those as opposed to this all items collection. So inventory item DTOs. So our getAsync method is ready to retrieve an improved set of items with name and description. And now it is time to do the proper registration in a startup to let our application know about this new catalog client that we're going to be using. So let's go to startup. And what I'll do is I'll open a little section just under our Mongo registration. So I'll do services.add HTTP client, and our client is going to be catalog client. Let's import missing namespace. And then I'll receive the specify parameter here is going to be the client. Okay, let's open that expression there. And here really the only thing that we have to specify for now is the base address of this other microservice, because otherwise how would it know? So we're going to say that the client base address equals a URI. Let's import a missing namespace. And then if you remember, the URI where our catalog microservice lives so far is a localhost 5001. So that's what you have to specify here, HTTPS localhost 5001. Okay, so this is a handy way to register our catalog client so that it can be used by dependency injection in other classes like in the controller, right? So you say add HTTP client, catalog client, and then you specify the base address. And then when that client is instantiated, it will automatically receive an instance of the HTTP client that you're going to be using to query for items. Okay, so with that done, let's go ahead and hit F5. Let's see this in action. Let's not forget to also do an F5 in our catalog microservice. So I'll go ahead and start also, here's catalog. I'll start it F5. And with the two services up and running, we can go ahead and go to Postman. And here in Postman, I am already in the tab for the operation that can retrieve all the inventory items for the specified user ID. So this is user ID that we used in the previous lesson. So let's see what information we can get now that we query the API. So we'll go ahead and hit send. And as you can see, we are able to retrieve the catalog item, but this time we not just have the ID of the item, we also have the name and the description of the catalog item. Okay, so this seems to be working pretty well. However, think about what would happen if the catalog service starts having issues, at least temporarily, or what happens if it's completely down. In the next lesson, we will learn about the problems that we might find when having a service communicate with another service. In this lesson, we will learn about partial failures in microservices and how to deal with them using timeouts and the exponential backoff technique. Even after placing our best efforts to ensure we have a healthy system, it is a matter of fact that in distributed systems, partial failures will happen. This could be due to multiple reasons, including network outages, hardware failures, dependency failures, and even routine things like having a deployment in progress. Regardless of the cause of the partial failure, when calling a dependent service, it could certainly cause our microservice to fail, which will end up in a bad experience for our clients. So, whenever a service makes a synchronous request to another service, there is an ever-present risk of partial failures, and so you must design your service to be resilient to them. One of the first things to consider when making requests to a dependent service is setting appropriate timeouts. A service client should be designed not to block indefinitely and use timeouts. Think about the experience of our client when the catalog service takes a long time to come back to our inventory service, if it ever comes back. Now the inventory service is also taking forever to respond to the client, leaving our users with a bad experience. And not only that, at least one of the threads of inventory is now busy not being able to serve any other requests, which reduces the amount of available resources in the service. Instead of this, you can set a timeout of, say, no more than 1 second, so that if catalog service takes more than that to respond, the request immediately fails, and the inventory service can in turn return the appropriate request to the client, even if it's a failure. This enables a more responsive experience and also ensures that resources are never tied up indefinitely. Like we mentioned, it is not uncommon for transient failures to occur in a distributed environment. Therefore, you usually want to give the dependent service one more chance to come back with a successful reply. However, you don't want to keep retrying at a constant rate, since that could overwhelm the dependency. A good strategy that you can use for retries is the one called retries with exponential backoff. This strategy performs call retries a certain amount of times with a longer wait between each retry. And here's how it works. As usual, the client will make a request to our service, and this one in turn will make a request to its dependent service. If this second request fails, instead of failing right away, our service will wait some time, and then it will try again. If the request fails again, we will now wait a longer amount of time before trying the request. If it keeps failing, we will wait a yet longer amount of time before one more try. And eventually, if we have tried enough times with no successful response, we will let the call fail. As you see, this strategy lets a failing dependency have an increasing amount of time to recover. It also avoids overwhelming the dependency. Let's see how to implement timeouts and retries with exponential backoff in our inventory microservice. Let's see our inventory and catalog microservices in action once again. So here I am in catalog, and I'll just hit F5 to start a web server. And then I'll go to inventory, and I'll do the same thing, hit F5. And now I'll go to Postman, and I'll try to get all the inventory items for this user ID. So I'll just go ahead and hit send. And here's what we expected to get, right? So the list of inventory items with name and description. Now, to simulate the effects of partial failures, let's first add a few temporal modifications to our getAllItems operation in Catalog microservice. So I'll go to our Catalog Visual Studio Code instance, and I'll stop it for now, close terminal, and I'll go to Items Controller, And what I'll do is I'll modify our getAsync method, the one that retrieves all the items, so that it introduces a few temporal failures for our inventory client. So before doing that, I'm going to add a little variable to track how many requests we have received from the client at this point. So I'll just add private static int. I'm making it static so that it doesn't reset after every request. Let's just call it request counter. Start with 0. And now in getAsync, I'm going to open space here. Let's go down. And I'll do the following. First thing that I'll do is I'll just increase the counter. And then let's add a log line just after this. Console.writeLine. We'll just say string interpolation, request counter, starting. So that's what it tells us, that it's starting a new request. Then what we're going to do is for the first 2 requests, we will actually increase, we'll add a delay to simulate the timeout scenarios. So if request counter less than or equals to 2, we're going to say, I'm going to copy this line here, console write line. We will say delaying, and I'm going to say await task.delay. This is how you can introduce a delay in the current request in an asynchronous way. Time span that from seconds will say 10 seconds. So the first 2 requests will be delayed 10 seconds. Then I'll copy this block here, down here, and we'll say that if the request counter is less than or equals to 4, what we're going to do is just return an internal server error, right? So to simulate that kind of error. So request counter, we will say 500 internal server error. And we will return status code 500. Now at this point, we are introducing this capability of returning either one result here or another type of result here. And in order to do that, remember that we have to switch from just returning the IEnumerable into returning an actual iAction result. So I'll say action result of IEnumerable of itemDTO, and I'll close this. So that gives us the ability to return more than one type of result. And also we'll have to modify our final return clause here so that it returns something that can be mapped to outcome result, like the OK result. And lastly, what we're going to add here, just over here, let me copy this console write line. This is going to be the happy path where we finally return something. And we're going to say request counter. We will just say 200. OK. Okay, so for a quick review, we have a static request counter. So every time a request comes in, it increases the counter. The first 2 requests are going to have a 10 seconds delay. The next 2 requests are going to end up in a 500 error. And then if we get past that, we'll get a 200 OK. And so at this point, I'll go back to our inventory. This is our inventory Visual Studio Code instance. I'll just stop it, close. And what I'll do is I'll first go ahead and collapse our navigation pane for now. I'll open my terminal over here. I'll open a new PowerShell terminal. And what I'd like to do is actually have 2 terminals in this window so we can see the interactions between microservices. So I'll use the split terminal icon here to open a second terminal. And in this one, I'll actually switch back to play the catalog directory. Okay. Play that catalog service. And here I'll do .NET run so that we can see the outputs that are coming out of catalog. And then on the left side, I'll start up our inventory microservice. Same way, I'll do .NET run. Okay, so with that done, let me go back to Postman and I'll try the query once again. So I'll hit send. And back in VS Code, you can see that now this first request is getting delayed. And now our inventory client is experiencing this significant timeout. if we try it again, from the point of view of Postman, so look at this, it just keeps waiting, waiting and waiting. We're giving a really bad experience to our clients, right? Okay, so what can we do about this? So the first thing, as we mentioned, is to introduce a proper timeout to avoid this kind of situation. So let's go back to Visual Studio Code. And what I'll do now is I'll stop both web servers. So I'll go to my inventory terminal, I'll do Ctrl+C, stop server, catalog, Ctrl+C, stop server. And what I'd like to do now is to add our reference to the Poly NuGet package. So this is the package that you can use in your .NET applications to properly handle transient error failures in a very easy way. So being in Play Inventory Service, I'll do .NET add package Microsoft.extensions.http.poly, enter. Okay, and then perhaps I'll put this back into place, and then I'll just do Ctrl+J to hide out terminals for a moment. Then I'll go to our Explorer and I'll go to startup.cs and I'll collapse this once again. We don't need it. And let's go into configure services. And yeah, so let's find the section where we are adding the HTTP client right here. And here what we're going to do is we're going to append yet another call to another method here that's called add policy handler. And here's where we can define a policy. So Poly has this concept of policies that different policies that can be used to handle different transient errors when you're invoking an external API. So we're going to use policy, and then let's import any missing namespace using poly. So we will say policy.timeoutAsync. And then we have to specify a type here, and that type is going to be HTTP response message. And let's add the system.net namespace, because this is the type of response I will get when you invoke the external client. So, and in this parameter, we want to specify how many seconds we want to wait maximum after calling an external API and before just failing. So I'll say 1 second in our case, and I'll close this. So just by doing this, you're saying that anytime we invoke anything under localhost 5001, we're going to wait at much 1 second before giving up. So let's see now how this works. I'll bring in back my terminals via Ctrl+J, and then I'll do .NET run in both cases. Okay. Perhaps I'll move this a little bit to the right. And then let's go to Postman and try the request once again. And as you can see, it now took just a little bit more than 1 second to complete the request. So instead of waiting for all those 10 seconds, wasting resources. Let's try again. Yep, and once again, it just took just a bit more than 1 second. If we go back to Postman, we can also see we tried the 2 requests on the right side, but then they actually took more time to respond. But regardless, we had already failed on the left side, on the inventory side. So that would at least help us fail fast to avoid the long delay and avoid consuming inventory resources unnecessarily. However, we note that transient errors are not uncommon in distributed systems. So we would like to not just fail right away, but instead try a few times, hoping for the catalog service recovery. In the next lesson, we will implement the retries with exponential backoff technique to improve our chances of succeeding in the presence of transient errors. In the last lesson, we introduced a 1 second timeout policy to our inventory microservice. Let's now use the retries with exponential backoff technique to let inventory retry the calls to catalog a few times before giving up. So here I am once again in the play.inventory microservice, and here's a line where in last lesson we added our timeout policy. What we want to do here is add yet another policy to specify what to do in the presence of transient errors and how to retry. So now I'm going to be adding that policy handler right here, just between the add HTTP client call and the add policy handler call. And just pay attention of the location of this, because we want to make sure that we can combine the timeouts with the transient error handling, so that anytime that we retry, we actually wait just 1 second, like specified in this policy. We wait 1 second between tries. if you don't do things in the order that are going to be shown here, that combination is not going to work properly. So at this location, I'm going to say add transient HTTP error policy. And let's actually go into the definition of this method for 1 second. So go to definition. So just so that you can see what this method is handling. So this method is taking care of network failures. It's also taking care of 500 errors, server errors, and 408 status codes, so request timeout. So this method we're going to use is very handy because it can handle all these situations by itself automatically. I'll close this. And again, notice the location where I added this. So now what I'll do is I'll say builder. And then we'll say builder dot wait and retry async. And here we're going to open parentheses, and we need to specify a series of parameters for this policy. And the first parameter is going to be the retry count. So this is how many times we want to retry in the presence of transient error failures. So for our case, let's say we're going to go for 5 retries. The next parameter is the sleep duration provider. So this is just a function that determines how much time to wait between each retry. So for this, we're going to say retry attempt, and then we'll use a time span class to specify a duration in seconds. But here is where the exponential backoff part comes into place. We're not going to just specify one specific amount of seconds. We're going to say mat.pow so that we can say, let's go for 2, and then we'll raise that into retry attempt. So this means that every time we're going to wait, we're going to be waiting an increasing amount of time that depends on the retry attempt. So for like the first time, it's going to take 2, raise it into 1, the first retry attempt. So 2 at 1 is going to be 2, so 2 seconds. So next time it's going to be 2, raise at 2, so it's going to be 4 seconds. Then next time 8 seconds. It will keep going that way in an exponential way, so that every time we just wait a little bit more. So that's exponential backoff piece of this technique. And then next, we're going to specify yet another parameter that you don't really need it, but we're going to use it just for the purposes of demonstrating what happens between the different calls. So you can totally skip this if you don't want to see what's going on behind the scenes. So I'm going to say on retry, and then we need to specify 3 parameters. It's going to be outcome, time span, and retry attempt. So I'll open this, and then here we can specify what we want to do each time that a retry happens. What we want to do is just present a log message in the console, and we can do we can use iLogger for this. Now, to do that, at this point, we need to actually get an instance of the iLogger class, but we don't have an easy way to do that right now. So what we're going to do is to, as an instance of the service provider, we're going to create a service provider, and from that one, we're going to get that service. This is not ideal, and that's actually going to present a warning message in the console, but we're doing this just for demonstration purposes, so totally avoid this technique in production code. So let's see, we'll say service provider equals services dot build service provider, and then we will say service provider dot get service. We want an iLogger of catalog client. Okay, let's see if we're missing a namespace. The extensions logging. Okay, so if you're able to get that service instance, so we'll use this question mark there. We'll say dot log warning, and here's where we're going to specify that message. And the message is going to be, and we'll do string interpolation here. We'll say lane for so many seconds, and those seconds are going to come from time span, the total seconds, and then making retry, and that's going to be retry attempt. Okay, close that, save. And one more thing that we have to do here is make sure that we combine both of these policies so that they can work together. And to do that, what we have to do is go back to this builder declaration here. and then we have to say builder.or, and then we specify the exception that will be coming out of the timeout async call over here. So in that case, that exception is going to be timeout rejected exception. And then let's see if we're missing a namespace using poly timeout. Okay, so that's how you can say that if the actual, and let's add missing parentheses, if we fail because of a timeout produced by the timeout policy, then it will fire a timeout exception. Let's go ahead and also retry. Okay, so that's the right way to combine both policies. Okay, so now let's just save this, and I'll open my terminals. And left side is inventory. I'll do .NET run. Right side is catalog. .NET run. Let's expand this a bit. And notice the warning that I was mentioning before. And this happens, like I said, because of the way that we're doing the service provider construction here. There's already a service provider built into the ASP.NET Core runtime. We're creating a second one. That's not ideal. But like I said, it's just for demonstration purposes. Feel free to remove this section in your production code. So now that we have both services up and running, let's go back to Postman. And let's go ahead and do a send to see what happens. So it starts, and going back here, you can see that first time we tried, and then we waited 2 seconds, then we waited 4 seconds, then we waited 8 seconds. We're trying to wait 8 seconds. On the right side, you can see that the multiple requests are coming in. Now they're firing internal server errors. And now we are in what's probably the last wait for 16 seconds. And so the client in Postman, as you can see, it just keeps waiting. It doesn't fail right away, but we are trying to get a chance to actually succeed. And yeah, eventually that happened. The client succeeded, and we no longer see an error. If we see back into Postman, we can see that, yeah, indeed, eventually we got a 200 OK for the last request, and it's looking great. Now, the one issue with this is that if you have multiple instances of your, in this case, of an inventory service calling a catalog, and they are all waiting exactly 4 seconds, exactly 8 seconds, 16 seconds between retries, that can actually cause a kind of bursts of calls into catalog service at the very same time, right? Because they're waiting for exactly the same time between retries. So to avoid overwhelming our catalog service, what we can do is introduce a little bit of randomness so that it is not exactly 4 seconds or exactly 8 seconds and stuff like that. So how can we do that? I'll do Ctrl+C in both of my terminals to stop those processes, and do Ctrl+J to close the terminals. And what we're going to do is add what we call a jitter. So this is going to be the way to add that randomness here. So I'll go up, and just over here, I'll introduce a random jitter. It's going to be new random. And then let's go back to the section where we're defining the retry attempt over here. And what we're going to do is just go to next line, and we will say plus time span that from milliseconds, and we will say jitter.next. And so we want to add is some number of milliseconds to those seconds. So we'll say any number from 0 to 1000 should be fine. So this time we should see that it's not just a specific amount of seconds, but those seconds plus some milliseconds that are going to be generated at random. So I'll save that, open terminals again, Ctrl+J, .NET run, and .NET run. Okay, and let's go back to Postman and try this again. So I'll hit send. Let's go back here. And as you can see now, we are not waiting just 2 seconds, but 2.5 to 3 seconds. And the next time we're waiting for that 338 seconds, and so on and so on. So with that, the different instances will be invoking back to a client at slightly different times, which lets a catalog not get overwhelmed. And so this is much better and would certainly help us handle temporal glitches when reaching out to the catalog service. However, imagine that a widespread network outage is preventing us from reaching catalog, or perhaps is preventing catalog from reaching its dependencies. So such outage would likely last, let's say, a half an hour. And if we have all of our inventory service threads retrying that much time, we may end up exhausting its resources. In the next lesson, we will learn more about resource exhaustion and how to deal with it via the circuit breaker technique. In this lesson, we will learn about resource exhaustion in microservices and how to deal with it using the circuit breaker pattern. Having a retry policy in place is good, but you also must be mindful about the limited resources available to your service. Imagine once again a situation where there is an ongoing issue with your service dependency. This might not be just a transient issue, but instead some prolonged downtime caused perhaps by a broad network outage. Now the client calls our service, and this one in turn invokes the already failing dependency, which will hopelessly start waiting for a reply. While this is happening, more clients keep sending requests to our service, and this results in more requests being sent to the failing service. One thing you have to realize is that each of these requests are making use of your service threads, of which there is only a limited amount. Once enough threads are in use, there are no more resources available, and you can reach what we call resource exhaustion. When this happens, your entire service becomes unavailable for any future requests, potentially causing a lot of trouble in the system. One approach we can use to properly handle this issue is implementing the circuit breaker pattern. A circuit breaker prevents a service from performing an operation that's likely to fail. Here's how it works. Once again, we are in a situation where our dependent service is already in a bad state, unable to provide successful replies. Our client then makes a request to our service. However, this time, instead of invoking the failing dependency directly, there is an intermediary that we will call the circuit breaker. The circuit breaker will now start monitoring the results of each of the requests that go through it to the external dependency. And when it detects that the rate of failure goes beyond the configured threshold, it will immediately stop letting any more requests go out and will fail them right away. This is what we call opening the circuit. After this, requests will just keep failing immediately during the configured wait time, which would hopefully give the dependent service enough time to go back to a healthy state. Eventually, the circuit breaker will let some requests go out to verify if they succeed. And if that is the case, it will close the circuit again, letting all further requests reach the dependent service. That's how the circuit breaker prevents our service from reaching resource exhaustion, while at the same time avoids overwhelming dependent services until they get a chance to recover. Let's go ahead and implement the circuit breaker pattern in our inventory microservice. To implement the circuit breaker pattern, all that we have to do is add a new transient HTTP record policy, just like we did for the wait and retry policy. So here we are again in the inventory microservice in the startup class, configure services method, and I'm going to scroll down a little bit here. And remember, we have already added a policy for wait and retries, and we have a policy for timeouts. So what I'll do now is I'll open yet another section here to add our next HTTP record policy. So I'll do add transient HTTP record policy. Remember that we want to do this just before the timeout and not after, so that this policy can also wrap the benefits of the timeout policy. So I'll open parentheses here, and what I'll do is I'll just copy this little section here so that we are properly combining this policy with the exceptions that could come out of the timeout policy. But then what I'll do is I'll invoke the circuit breaker async method here, and I'll open parentheses. And here we have to specify the parameters for circuit breaker. So the first parameter that we have to specify here is how many tries we're going to allow, or how many requests we're going to allow through the circuit breaker before the circuit has to open, right? So in our case, let's say that's going to be 3. So 3 failed requests are going to go through the circuit breaker before the circuit breaker actually notices that, yeah, there's a problem and we have to open the circuit. Next comes the duration of or time span of the break. So this is how much time we will keep the circuit open. So let's say this is going to be time span from seconds, let's say 15. And that's really most of what you have to do. You don't have to do more than that to enable the circuit breaker. But just like we did with our retries, let's add a couple of functions here to get an insight of what's going on behind the scenes. So what I'll do is I'll say on break. So this is a function that will be used when the circuit opens. So I'll say outcome and time span. Okay. So in this case, we want to add a log message and stating that the circuit breaker is opening. So this is going to be really very similar to what we did for our wait and retry. So I'm actually going to copy these 3 lines from here. I'll copy them over here for our onBreak function. And I'll just change the message the following way. So I'll delete this and I'll say opening the circuit for, and this is going to be time span that total seconds. Okay, so that's what's going to happen when the circuit breaker opens. And then next, we're going to add another one for the onReset function. That's not going to receive any parameters. And in this one, we're going to do something very similar. So I'll copy again those lines, paste them there. And in this case, we're just going to say closing the circuit. Okay, so that's really all you have to do to enable the circuit breaker. So again, we are waiting. We will allow 3 requests to go into the circuit breaker, and if those 3 are failing, the circuit is going to open. Then it's going to wait 15 seconds before allowing any new request to actually try to reach the other end. During those 15 seconds, things are going to just fail right away. And then we have functions to log what's happening when the circuit opens and when the circuit closes. So now I'll go ahead and I'll open my terminal. So I'll save this file. I'll open the 2 terminals. Just like in previous lessons, I have 2 terminals. Inventory service on left side, catalog service on right side. I'll do .NET run in both sides. Okay. Notice we keep getting these warnings about the build service provider issue that we talked before. But like I said, this is just for demonstration purposes. So now I'll get back into Postman and we'll try out that inventory API to get all the items in the user's inventory. See what happens. So I'll just go ahead and hit send. And notice on the left side that we failed. So we waited for 2.002 seconds. Then we tried, failed, waited for 4.644 seconds. And then at that point, the circuit actually opens for 15 seconds. So we're waiting 8.71 seconds for the next try. But the moment that we try this again, things failed right away, as you can see on the left side. And if we see what's happening in Postman, yeah, we're getting that error. The circuit is not open, is not allowing any further calls. And if we try once again, it may take 1 or 2 seconds, but it will fail because the circuit is open. And if we just keep trying and keep trying, we're getting an immediate result. So this is the effect of having the circuit open. So any new requests that are coming here from any client into our service are going to fail right away. However, eventually the circuit lets us go through one more request. And if it notices that it's successful, it opens the circuit like it happened right here. If we go back to Postman, we can see that it allowed one more request just to see if things are healthy once again. And it got a 200 result. And then it said, yeah, closing the circuit, and it allowed things to keep working once again. So that's how the circuit breaker works, and that's how it can help us prevent overwhelming other services or having to waste resources and cause resource exhaustion in our microservice. At this point, we are doing a fairly good job at handling partial failures between our inventory and catalog services. However, could there be a better way to have inventory get all the information it needs from catalog without having to rely on catalog to be available most of the time? In the next module, we will learn about the asynchronous communication style and how it can help us enable a much more resilient communication between our services. In this module, you will learn about the asynchronous inter-service communication style, the challenges it can help solve, how to implement it via RabbitMQ and Mass Transit, and how to enable eventual data consistency between our two microservices. By the end of this module, you will have a solid understanding of the following: the basics of and when to use asynchronous communication between microservices, how to enable microservices autonomy and the impact to the SLA, how to use a message broker for asynchronous data propagation, how to stand up a RabbitMQ message broker via Docker Compose, how to publish messages to RabbitMQ via the Mass Transit framework, how to consume messages from RabbitMQ using Mass Transit, and how to implement eventual consistency of data propagated across microservices. In terms of our overall system design, in this module you will stand up a RabbitMQ server to act as a message broker that will store asynchronous messages in queues. Then you will update the catalog microservice to start publishing messages anytime the catalog of items is updated. After that, you will modify the inventory microservice to asynchronously consume these published messages and store the corresponding item information into its local database. And finally, you will update inventory to stop making synchronous calls to catalog and instead take advantage of the new catalog information stored in its local database. Let's get started. In this lesson, we will learn about the asynchronous communication style and how it can help us enable much more resilient communication between our services. Imagine a scenario where after receiving a request from a client, our microservice needs to reach out to two other microservices. Also, each of these services need to get in touch with other services, which in turn might need to further reach to more services. There may also be services that depend on the services that our service depends on. We originally fine-tuned our service so that it never takes more than 300 milliseconds to respond to our client requests. However, when we started making synchronous calls to one of our dependent microservices, we had to add to our time the 200 milliseconds that service can take to respond. That was still okay in the beginning, but unfortunately, when that dependency eventually started calling another dependency, and that one yet to another one, our overall average latency bumped to 1,450 milliseconds, which is bad. On top of that, if one of our deeper indirect dependencies starts failing, even if temporarily, it can cause all of the services that depend on it to also start failing. And the effect keeps cascading until potentially most of our system becomes unavailable. One important concept that you should keep in mind as you embrace microservices is the Service Level Agreement, or SLA. The SLA is basically a commitment between you as a service provider and the client. For instance, as part of our SLA, we could have defined that our service can be expected to be up and running 99.9% of the time. So, when our clients choose to use our service, they should expect it to be down approximately 44 minutes during the month, which the owners of the client will have to decide if it's acceptable. However, when using synchronous communication, calculating such numbers for our service SLA gets more complicated. Our deepest dependency is also advertising a 99.9% uptime in their SLA. And let's say that all of the services initially advertise that same value. However, in our scenario, when dependency 4 fails, it impacts the SLA of dependency 3, which now sets its SLA down to 99.8%. This in turn impacts the SLA of dependency 1, and ultimately impacts our own SLA. Now, with an SLA of 99.6% uptime, our clients would be subject to about 175 minutes of downtime across the month, which is way below of what we wanted to provide initially. So the synchronous communication style suffers from an increase of latency due to the chain of calls. It can significantly amplify the impact of partial failures and can potentially reduce the SLA of our service. Now, let's look at the asynchronous communication style. Here, the client does not have to wait for a response in a timely manner. And in fact, depending on how the communication has been set up, there might not be any response at all. To enable such communication, there is usually an intermediary called the message broker, which is pretty dumb in nature, meaning that it has no business logic on it, and it is also highly available. With the message broker in place, the service client sends messages to the broker and the broker forwards the messages to receivers as soon as possible. The messages can be received by two types of receivers. A single receiver, in which case we think of the message as a command via which the client requests an action on the receiving service. For instance, when a purchase operation starts, our trading service will send a command to our inventory service asking it to grant items to the user's inventory, and another command to our identity service asking it to debit yield from the user. We could also have multiple receivers, where there are multiple services that subscribe to the events published by the client service. This would be the case if, for instance, our catalog service would like to publish any updates to its catalog of items so that other services can be informed about the changes. One of the key benefits of using asynchronous communication is that it enforces a microservice's autonomy. Let's see how it's enabled. In a single receiver scenario, we would have again our client talking to our service, but our service will not talk to its dependent service. It will instead send an asynchronous message to a broker, and it will immediately acknowledge to the client the successful reception of the request. The dependent service will consume this message from the message broker as soon as possible and will eventually provide a reply via the same broker. At that point, the client can request the status of its initial request to our service, or our service can notify the client of the response. All of the services in our system would follow the same message-based approach, including cases where a reply is not required from the called service. The great thing about this kind of layout is that when one of the dependent services fail, it would not cause any impact on the other services, since all of them have been decoupled from each other and only talk to the message broker. So the same SLA that one of the services presents can be honored across the entire system, assuming that the message broker offers high availability. So, with asynchronous communication, partial failures are no longer propagated. Each service has its own independent SLA, and best of all, the autonomy of all microservices is enforced given the lack of coupling between them. One of the nice things that asynchronous communication provides is the ability to asynchronously propagate data across services. In the synchronous communication scenario, when the client requests the user's inventory, and since the inventory service only has the data that's relevant to it, inventory has to first talk to the catalog service in order to retrieve additional details about each item. How can asynchronous communication help here? Well, thanks to the presence of the message broker, what we can do now is have the catalog service publish an event each time a catalog item is created, or updated, or deleted. Such event doesn't have to have all the details of each item, but only the ones of interest to client services. We can then have our inventory service listen to these events and create its own collection of catalog items in its own database. As long as we have a highly available message broker, the list of catalog items in the inventory database should be eventually consistent with regards to what's in the catalog service. Now, when the client requests the user's inventory has no need to go out into any dependent service to request item details. It has everything it needs in its own database, and it can immediately provide a reply to the client with no additional latency. So, thanks to asynchronous communication, we can enable eventual consistency across our system, the autonomy of our services is preserved, and the previous inter-service latency is reduced or completely removed. In the next lesson, we will start implementing asynchronous communication between our two microservices. We will introduce RabbitMQ as our message broker of choice, given that it supports the AMQP protocol. It is lightweight, easy to run locally, and is very popular in the open source community. RabbitMQ introduces the concept of exchanges, which you can compare to a mailbox. When a service like Catalog needs to publish a message, it will send it to an exchange in RabbitMQ. And with the appropriate bindings in place, the exchange will distribute the message to any of the configured queues. From there, RabbitMQ will take care of delivering the message to any subscribed services like inventory. We could use RabbitMQ directly in our code, but we would first need to create the exchanges and queues and configure the bindings to ensure messages are properly routed. Also, our code will be tied to RabbitMQ, and if we ever wanted to move to another message broker, we would need to rewrite a good part of our services code. For this and a few other reasons, we will instead use Mass Transit on top of RabbitMQ. Mass Transit is a popular open-source distributed application framework for .NET. Mass Transit can take care of doing most of the RabbitMQ configuration for us and is able to integrate with multiple other message brokers while allowing our services to stick with a higher layer of broker-agnostic APIs. As part of this, Mass Transit introduces the concept of a publisher and a consumer, which is what our service code will focus on. Let's start coding. Just like we need to define DTOs to establish contracts between our REST API and our API consumers, we also need to define the contracts that define the messages to exchange between services that use asynchronous communication. However, this time we will define the contracts in a separate project, mainly because we will later package and share the contracts with other services so that they can easily use them. So let's start by defining the contracts that our catalog service will use to send events asynchronously anytime an item is created, updated, or deleted. So here we're back in the play.catalog directory. And what I'm going to do is I'm just going to open up my terminal, Ctrl J, and I'm going to switch into the SRC directory. And right here, what I'm going to do is just create a new class library. So let's do .NET new class lib, and we'll give it the name of play.catalog.contracts. Hit enter. Okay, and our brand new project has been created over here, as you can see. Now, the first thing that I'll do right away is to open up my project file, and just like we did with the other projects, we're going to be removing the implicit usings and the nullable settings here, because like I said, we are going to cover those at the very end of this program, right? We are not covering that here. So I'll close that. And then, before we forget, let's also go ahead and get a reference from our catalog service project into our contracts project, so that the service project will be able to start using those contracts right away. So I'll just switch into play.catalog.service here. And here what I'll do is add a reference via .NET add reference. And then we'll go into play.catalog.contracts, play.catalog.contracts.csprog. Hit enter. Okay, and what that does is that in the csprog file for the service, you will see now we have this new reference over here, this project reference, which means that the service project can now use any types that are defined in the contracts project. All right, so now let me close this. And then let's go into this contracts project. So the first thing to do here is to get rid of this class 1 that we are not going to be using. So just delete that. And then I'll go ahead and right click in the play.catalog.contracts directory. I'll say new file. And this file is going to be named contracts.cs. Okay, so let's give it a namespace. So it's going to be namespace play.catalog.contracts. All right. And here we're going to define one record for each of these interesting events. Right. Now, one thing to remember here is that we don't need to define every single property of the catalog item object in these events. Only we need to define here the properties that are of interest of our consumers, right? So for instance, if we define public record catalog item created, the properties that we're going to define here is what really matters for whoever consumes this event here. So for instance, likely the item ID will be of interest. So item ID. Then we'll also get the name. And let's also add the description. Okay, those are the only items that we're going to define for this event here. Now, just like we did this, let me go ahead and define one more entry for catalog item updated. Okay, and for this one, we're going to define exactly the same properties, item ID, name and description. And lastly, we're going to define public record catalog item deleted. Now, in this case, really the only thing that we need to communicate would be the item ID. So I'll say GUID item ID. Now at this point, I'll just go ahead and do Ctrl+Shift+B to make sure that things are compiling. I think we're missing using a statement here. So yes, so the IDE, VS Code just detected that. We're missing an import for GUID. So I'll do Ctrl-. And since I'm not seeing the element here to import a missing statement, what I'm going to do is just Ctrl+Shift+P, and I'll do OmniSharp, restart OmniSharp, right there. So that will restart the OmniSharp server, and hopefully it will help us identify the missing usings. So it just restarted. All right, so let's go ahead and try this out once again. I'll do Ctrl-. And as you can see, yeah, now we got it, using system. That's what we're missing here. All right, so let's build this again, Ctrl+Shift+B. Yep, everything is building successfully now. All right, so with that, we have our items defined, our items in our contracts defined for the catalog item. And so in the next lesson, we'll update the catalog service to start using these contracts and a few new NuGet packages to start publishing messages to a service broker.